Integrated Circuit 6, Analog Circuit, Op-amp Part 3. Now the op-amp is often used to amplify the small signals. It's like audio signals, video signal, and any others microwave signals. If the IC chip can keep up with the frequency, the op-amp is an important part of the entire electronics design. Now, in order to understand how to use this for small current signals, we need to understand the equation for the bipolar transistor. Now, Dr. Shockley, he moved from East Coast to West Coast and stayed in California, started the silicon chip company. After that company's resolved, so many different IC chip company appeared. That's the beginning of the Silicon Valley. And Dr. Shockley summarized his all the findings in the book, the famous Dr. Shockley's semiconductor book. In there is a diode equation, Shockley diode equation, and this become the base for transistor, understanding transistor. Okay, basically there is a intrinsic voltage Vt equal kT over Q. K is a Boltzmann constant, Q is electron charge, and T is absolute temperature, and IE is expressed by this equation. This is the diode equation, but it's applied to the transistor because this part is like a diode, and the IE is given by this. Now the Vt increases as temperature goes up, but this is so-called dark current. It's highly temperature dependent. So when the temperature goes up, then this IE increase. So relationship between IC and IE is given by this alpha. Okay, and since this IB is remaining of the difference between IC and IE, IB becomes beta IC. Okay, so this beta increase as temperature increase, then VVE decrease to keep up with the same current if current is given here. Okay, those are basic characteristics of transistor. Okay, so the transistors is highly temperature dependent, and often we have to consider that and compensate for temperature in the analog circuit, and that's what we talk about. Beta is function of temperature T. Another things we can do is for the very small current, we can use the super high beta transistor. It's called the Darlington pair. It can be even down to 10 picoamp, and 10 picoamp is amplified by beta 1 times beta 2 up to 100 microamp, which is comfortable range to handle in the bipolar circuit. So this kind of device IC chip can use to handle the very small signals. It's called the super beta transistors, and make the emitter size as small as possible. The technology can allow, so they increase the current density to pick up the effect of a small current. 10 picoamp is really small, and any wire inducted current can be picoamp level, okay, by the microwave. So this also provides a relatively high input impedance, so the input current is not get lost. Another problem we have to consider is there is a parasitic capacitance between emitter and the base, and base to collector, and there are some between emitter to collector. Those parasitic capacitor is going to act in the small signal and the fast high frequency. The problem is beta start eroding at the higher frequency because this the switching speed, this very minor capacitor, but its capacitor become very the effect of a capacitor comes into the play at the high frequency, and it lose transistor's characteristic, so the beta start decreasing. So you have to know the beta is also the function of frequency. When the frequency goes high, then beta decrease, and this is Bode plot. Bode plot is they talk about the gain by frequency. And also there's another chart called phase. Phase also change for the AD current. But let's see, when you handle the higher frequency, the emitter sides become critical. Okay, that's what you have to remember in the IC chip design. And there's another consideration, is called the through rate. The op amp, if you look at the data sheet, they talk about through rate, and what it is when you give clean wave as input, the output supposed to be like this, but it start having this ringing effect. Okay, jittering, some people call jittering or ringing. This happen when the gain beta, the phase, the AD signal is a complex numbers, has absolute value, the beta, and also has the phase start changing. And when the phase start changing to more than 90 degree, then it starts showing the oscillation, small oscillation here, but it's attenuate, oscillation attenuate, it's settled. Okay, now through rate is when you give this step function how fast it goes up, and that's depend on the charging speed of the capacitor around the transistor, this capacitor, right? So if emitter size is small, parasitic capacitor is small, so through rate is much higher. It can stand up really high, fast. Okay, so op amp can follow the input, almost perfect shape, or maybe some ringing, the jittering effect here. But the slow op amp is going to be like this, right? And the speed, it still have this jittering effect. Now it's nothing to do with the through rate. Through rate is somewhat independent from this, the gain. So that's what we have to consider in analog design. Another thing is ground guard line. And this is necessary when you deal with a small current line. If this is a small current here, and around here it's all like a small current circuit, you need to make sure we put the ground metal on the silicon to isolate them well. Okay, because any effect, the radiation effect from this one is kind of absorbed by the ground line, so interaction between them is going to be eliminated by this ground line. And in this area, when the signal is like a picoamp to 1 microamp, the avoid multi-layer no parallel line overlapped. Okay, if you do multi-layer, it's okay to have minimum overlay, right? So layout become very crucial in the analog design because current is so small, it's easily affected by the neighboring wire and become the feedback, unwanted feedback signal. Okay, that's very important. And finally, you have to know the silicon resistor. Say N well, you tap into here, so this is going to be the resistor. Now, in reality, this resistor whole thing is like a diode reverse mode. So there is some leak current here. So when you have a current going through the resistor A and B, you have to consider how much the leak current is. If leak current is bigger than this current, it's going to screw up the entire circuit. Okay, so for small current circuit, we have to be careful. It's not like a discrete circuit design. You have resistor here on board and it's totally isolated from input circuit to the output circuit, and no current loss. And that's not the case for the IC chip. IC chip, all the resistor is reverse diode, and there is some leak current. Okay, the leak current is diode characteristic like this, and some leak current here. And it's not the issue when the current is large enough, like 100 microamp to 10 milliamp. It's not a big issue, but when it's come to pico, then it's become a very big issue. So whole circuit has to be created to consider this possibility of leak current, and layout has to be very carefully made. Okay, so that's the tips for the analog design on the silicon chip. If you like, you can hit subscribe.